curious mind embraces wonder and the desire to understand. It's always seeking, always learning, and always growing. RFC 7432 introduces a versatile and adapting multi-homing EVPN solution that functions over an MPLS IP network, enabling seamless communication between host or CE devices within the same subnet. However, in situations where two distinct layer 2 networks need to communicate, routing can be utilized as a suitable alternative. This becomes particularly relevant when components such as storage, web, and application resides in separate layer 2 networks that are isolated from each other. To effectively handle such scenarios while retaining the multi-homing capabilities of EVPN, the integrated off-layer 3 gateway devices becomes crucial for efficient inter-subnet connectivity end systems. This connectivity is achieved through a technique known as integrated routing and bridging, which relies on layer 3 gateway devices. The specification and details for this approach are outlined in RFC 9135. Hello friends, my name is Sabi. In today's video, we will explore fascinating topic of integrated routing and bridging in the context of EVPN. This technique plays an important role in facilitating communication between different layer 2 networks. Specifically, we will delve into how layer 3 gateways devices come into play to enable seamless connectivity between different layer 2 networks. For more in-depth information, you can refer to RFC 9135 and RFC 9136. So join me in this educational video as we unravel the concepts behind integrated routing and bridging and its significance in facilitating inter-subnet communication within EVPN. So in the conventional network setup, when host 1 intends to establish a communication with host 2 within the same subnet, it directly transmits the traffic through the layer 2 switch. However, in the case of communication between host 1 and host 3, known as inter-subnet communication, the packet destination MAC address is set to the default gateway router MAC address, while the destination IP address is configured as 20.1.1.40. Subsequently, the packet is routed based on the lookup in the routing table to reach the host. So the routing in the Ethernet virtual private network based on the MAC performed the similar bridging like in the switch 1 in the traditional network, so which we called as a MAC VRF. The routing process can be an IP VRF, and the IRB, which stands for Integrated Routing and Bridging, a MAC VRF connects to the routing process via a virtual port, is called as IRB interface. And the IRB interface acts as the IP address, or you can refer to as SVI for that VLAN. It has an IP address and a MAC address. So it's similar like a traditional inter-subnet routing. Layer 2 header strips by the IRB interface as the packets are forwarded to the routing process. It is similar like a traditional inter-subnets routing. So layer 2 frames received on the MAC VRF with the destination MAC address of the IRB interface and forwarded to the routing process. So the IRB interface, which is the integrated routing bridging, is act as a default gateway in our traditional network. So the layer 2 header strips by the IRB interface as the packet forwarded to the routing process. When the routing process receives the packet is routed to the destination according to the original IP address. The integrated routing and the bridging provides an optimal forwarding model and avoids traffic thromboning. And this has been divided in two parts, which is asymmetric IRB forwarding model and a symmetric IRB forwarding model. In this scenario, where two hosts are linked to the same leaf but belongs to distinct VLANs, the packet journey between host 1 and host 2 we will able to analyze and able to understand what happened exactly in a virtual world. Initially, the packet reached to leaf 1 carries the destination MAC address, which is the corresponds to the VLAN 10 IRB. The layer 2 overhead is removed and the packet is then directed to the IRB for routing process. An IP lookup is conducted on the IP header, after which the packet is sent to the destination VLAN 20, where the routing process performs a lookup in the ARB table for VLAN 20 on the destination IP address, which is 21.140, and the lookup returned with a MAC address of host 2. Subsequently, a layer 2 header is appended to the packet and featuring a source MAC address specific to the VLAN 20 IRB, and the leaf then process and forward the packet towards the intended destination. So the integrated routing and bridging provides an optimal forwarding model and avoids traffic thromboning. That has two parts, which is an asymmetric IRB forwarding model. In asymmetric IRB forwarding model, the ingress and the egress VTEPs behaves differently. The ingress VTEP, which is also the first hop router, does a routing lookup to decide which is egress VTEP. The inner packet is then addressed to the final destination. So generally, the ingress VTEP will do a routing lookup, whereas the egress VTEP will do only bridging. So the name asymmetric routing, this model assumed that the destination network is local to the ingress VTEP, else it could not know the MAC address of the final destination. So whereas on the other hand, we will have symmetric IRB model in which the ingress as well as the egress VTEP route the packet to the final destination. So now we will deep dive in each of this model. So at the source, the packet is directed into the destination VLAN through the routing. Subsequently, these packets are VXLAN bridge to reach the destination leaf 2. Upon arrival at the destination leaf, they entered an intended layer 2 segment. Here they bypass the routing process on the remote leaf and immediately directed to the MAC VRF to forward the packet to the destination. Now we'll see the packet walk in asymmetric IRB model. So in general, we have two VTEPs. In VTEP 1, we will have host 1 in VLAN 10 intend to communicate with host 4 with VLAN in VTEP 2. So when a packet enters the MAC VRF with a destination MAC address of IRB interface, the MAC VRF strips off the MAC header, and then it forwards the packet for the routing process. In the routing process, it performs a lookup on the destination IP address of 21.100, which is host 4. Essentially, the concept to grasp here is the key differentiation. The conventional routing process cannot solely route the packet to the VXLAN requirement for an inner layer 2 header. So the routing process has to build the inner layer 2 header first in order to send the packet through the VXLAN tunnel. So the routing process necessitates the reconstruction of the inner layer 2 header. This achieved by conducting a lookup in the adjacency table to identify the MAC address associated with the destination IP address of 21.100. For this table, the learning process has already been done with the help of route type 2. So this determines the MAC address will serve as a destination MAC address of the new layer 2 header, which is obtained from the ARP table. Meanwhile, the source MAC address will be extracted from the MAC address of the IRB interface 20. The packet is then passed to the VTEP, where the VXLAN header is added and the VNI is set to the appropriate value of the layer 2 segment. The destination IP is the remote VTEP found in the IP verf lookup, and the source IP is the local VTEP. And then we will have our MAC information, VTEP 1 as a source and destination as the next hop, as let's say spine. So when the VTEP 2 receives the packet, it removes the outer MAC address and the IP address, then removes the VXLAN header, and then it passes the packet to the MAC verf specified by the VNI value as 20. Based on this VNI value, the MAC verf performs a lookup to the destination and forward the packet. So what we learn from the asymmetric routing? Asymmetric routing IRB depends on the three tables: the MAC verf forwarding table, the VPN adjacency ARP table to rebuild the inner layer 2 header, and the routing table. So the VTEP learns the MAC and IP address of a remote host via route type 2. So the host MAC address is installed in the MAC verf specified by the VNI in the update, and the next hop is set to be as remote VTEP plus the VNI. So when the IRB interface is defined on the leaf, the IRB subnets is added to the local routing table on the leaf. Once the subnet is in the local routing table, the packet can be routed between the IRB interface on the leaf itself. That brings to the end for the concepts of asymmetric routing, but there is some limitations associated with asymmetric routing. So in asymmetric routing, packets are bridged after routing. For instance, when destination network is local to the ingress VTEP, the ARP&D table includes all remote endpoints, and these entries are consequently reflected in the MAC forwarding table. So the challenges for this: learning the remote IRB MAC address, scaling limit for VNIs, explosion of IRB next hop MAC addresses. To encounter these challenges of asymmetric routing, symmetric routing is employed. In symmetric routing, the behavior remains consistent for local destination networks. However, the non-local destination network, the routing table encompasses all remote endpoints such as /32 host routes along with the respective egress VTEPs on the. So as a result, the MAC forwarding table solely contains a single MAC entry that of an egress VTEP from perspective of VNI scalability. Symmetric routing outperforms asymmetric routing. This is due to each VTEPs only needing to manage the VTEPs it is concerned with while still facilitating connectivity to non-local VNI. Now we'll look at it, the symmetric routing. If you remember, asymmetric routing, the ingress VTEP routes and the egress VTEP bridge. Whereas in the symmetric routing, the ingress as well as the egress router routes the packet to the final destination. So the packet forwarding in symmetric routing differs from the asymmetric routing in three different ways. First, the ingress VTEP routes the packet to the final destination with the egress VTEP as the next hop. Second, the egress VTEP, after decapsulating, does a routing lookup to decide the packet to the final destination. Third, the VNI used to carry the packet between the ingress and the egress VTEP is an layer 3 or a VRF VNI. So the layer 3 VNI is different from layer 2 VNI of the source or the destination network. Symmetric IRB works by adding a IP VRF to the data path on both the source and destination leaves. This means that the destination IP address is responsible for building the layer 2 header. So this solves basically the VNI scaling limit. In symmetric IRB, the routing process is typically an IP verb. It allows each tenant to have their own routing process. So the IP verb has its own VXLAN tunnel. The traffic bridge within this same layer 2 segment uses the VNI for its layer 2 segment. The traffic between the layer 2 segment uses the IP verb and the IP verb VNI to reach the remote IP verb. The symmetric IRB has one additional change over the asymmetric IRB. A system MAC is simply a chassis MAC is used here. The source, the route also needs to carry the egress VTEP MAC address because this address is used as the destination MAC address of the inner packet. So this MAC address is carried in the new BGP extended community in the advertisement. This new extended community is called router MAC extended community. This MAC extended community is used to carry the P or the leaf MAC addresses for a symmetric IRB scenario. So why we use the system MAC here? The source VXLAN encapsulation requires an inner Ethernet header. If you remember from the asymmetric, whenever we are doing a VXLAN encapsulation, we need an inner MAC address. By that way, in asymmetric, we do that in a source VTEP itself. But in case of symmetric, we need a MAC address. So the source VXLAN encapsulation requires an inner Ethernet header. And since the tenant MAC cannot be used in the inter-subnet traffic, the source VXLAN encapsulation requires an inner Ethernet header. And since tenant MAC cannot be used for inter-subnet traffic, so the ingress VTEP or the leaf MAC address is used, and it is common across all MAC and IP verbs. So the MAC information need to advertise using EVPN route extended community. So in symmetric IRB, the source leaf is routing to another IP verb, not a MAC verb. This means that IP verb does not know the MAC address of the destination host. So in symmetric, layer 3 subnet and the IRB interface corresponds to the MAC verb are required to provision at the leaf or the PE only if the PE or the leaf has locally attached host in that subnet. Now let us see the packet walk between the two VTEPs with from host 1 to host 4, from VTEP 1 to VTEP 2. Host 1 sends a packet towards default gateway, the IRB interface MAC address. When the IRB interface receives the packet, a lookup on the destination IP has been performed in the IP verb. The lookup returns the destination VTEP and the VNI and destination leaf system MAC address. Let's go through the packet walk in order to understand more about the symmetric routing. Host 1 sends a packet to its default gateway, the IRB interface. When the IRB interface receives the packet, it's dual lookup. So lookup for the destination IP address. So the lookup returns the destination VTEP, the VNI, the destination leaf, and the system MAC address. The inner layer 2 header rebuilt using the system MAC address of leaf 1 as a source MAC, the system MAC address of leaf 2 as a destination MAC. The VTEP adds the VXLAN header. The destination IP address is VTEP2, VNI 20. We will have inner MAC address as leaf 2 router MAC. So when the destination leaf receives a VXLAN frame with an inner destination MAC set to as leaf of the system MAC, the leaf knows that the packet must be sent to IP. The VTEP strips the VXLAN header and the inner MAC header, forwards the packet to the IP verb. The IP verb does a recursive lookup in the MAC verb 20 ARB table to resolve the destination MAC address of destination IP 21100. Rebuild the inner layer 2 header, read out the packet in IRB 20 to the destination host 4. The symmetric IRB resolves three major shortcomings of symmetric IRB by adding an IP verb on the leaf. So learning the remote IRB MAC, VNI scaling limit, and IRB next hop MAC table explosion. In order to enable inter-subnet routing across leaf in a deployment where not all subnets are provisioned at the leaf participating in a EVPN, so IRB instance leaf must advertise a local subnet routes, which is route type 5. So these subnets are required for a bootstrapping host IP MAC learning using the gleaning procedure initiated by an inter-subnet data packets. If you remember, L3 VPN supports routing protocols between VRF, IP verb, and a router running in the host network. So this allows the tenant or the CE router to advertise the routes to the EVPN domain and the EVPN domain to advertise the routes to the tenant routers. In order to exchange the routes across EVPN domain, IP verb must be stretched across EVPN domains. Stretching an IP verb simply means that EVPN type 5 routes updated are used to advertise layer 3 subnets learned from tenant router or the CEs to the remote VTEPs. So route type 5 routes are used to advertise layer 3 routes and the subnet. These routes are not bound to any host MAC address. Whereas the type 2 routes can send IP address, but those IP addresses are bound to a specific MAC addresses. So they are full /32 addresses, not the subnets. The BGP route keys for route type 2 update uses the MAC address and the IP address. BGP uses route keys to compare the route MAC addresses, should not use to compare paths to an IP subnet. Separating MAC functions from IP functions. Advertising IP prefixes in route type 5 updates allows leaves to process subnets separate from MACs. So advertising the same MAC for multiple ESIs as well. This implement also in the floating IP concept. To move the IP to a new subnet, to move the IP to a new host, change the MAC, the IP address must be decoupled for the MAC address. So the stretching IP verb with EVPN, in order for a layer 3 routes to exchange between the IP verb on the remote leaves, the IP verb must be stretched across EVPN and advertise the route type 5 in order to build the control plane. The symmetric IRB stretch the IP verb across leaves. So stretching an IP verb simply means that use of route type 5 or 2 to update and exchange routes between the leaf using IP verb. So the route type 2 and route type 5 updates are the dynamic routing protocol as like in L3 VPN. Depending on the existence and the characteristics of the SBD and the IRB interface for an IP verb, there are two IP verb models that is defined in RFC 9136. So first one is interfaceless model. It is like a plain vanilla way to implement EVPN stretch like an L3 VPN. So we will have a tunnel across IP verb to IP verb. Then we will have interface full with an SBD IRB model, which requires an SBD as well as gateway IP address as an overlay index. So the SBD stands for a supplementary broadcast domain, a broadcast domain that does not have any attached circuit, only IRB interfaces, and is used to provide connectivity among all the IP verbs of the tenants. So the SBD is only required in IP verb to IP verb communication. So the third one is interface full with an unnumbered SBD IRB model requires the supplementary broadcast domain as MAC address as a overlay indexes. So we'll discuss this further in our next video about the interface less model, interface full model, and interface unnumbered. So what all we covered in this module is basically we started with the traditional networking. With traditional networking, if we enter into the virtual world, how it will look like, what is MAC verb, what is IP verb, what is a bridge domain, and then IRB routing. We have IRB forwarding model. We have two types of IRB forwarding models, that is asymmetric IRB and symmetric IRBs. And then we have seen that the route type 5, and with the route type 5 there are three different models that we will have with IP verb to IP verb, which is interface less model, interface full with SBD IRB model, and interface full with an unnumbered SBD. So we'll look in more details of route type 5 with these three models in our next video. Thank you for joining us in the exploration of the route type 5 and integrated routing bridging with EVPN. If you found this video insightful, don't forget to like, share, subscribe, and hit the notification bell for more valuable content. Stay connected with our community by clicking in the description, and let's continue the fascinating world of technology together. Until next time, thank you so much.